Hi, welcome everybody. First of all, I'm very glad to be here. It has been a great conference so far, so congratulations to the organizers. Yeah, I'm Martin Benedikt. I am a data scientist and I work for HOPR, and today I want to talk about privacy via noise and incentives. Up front, let me tell you that HOPR is working on transport level privacy. So what you should imagine during the talk is that we're doing something like a Web3 version of a VPN. Because a VPN is what you already know from how you transmit data without leaking your privacy. And let me depict what I call our naive little wonderland, where we as the users, the typical users of Web3, interact with the infrastructure and the services that it provides on a daily basis, because it provides the freedom of choice, inclusion of everybody, but without actually proper transport layer privacy, for example, our metadata, and including our metadata, for example, our IP address is exposed, where our IP address is the single most important identifier of our identity. And this has been used this information about our metadata can be used to censor the user and the services that we like to use. And we at HOPR, we built like a decentralized and incentivized mixnet to basically obfuscate all kind of metadata to basically ensure that no third parties like RPC providers know about your, for example, metadata and IP address, to basically obfuscate all communication traffic so that you, as a user, can send transactions privately on the blockchain without leaking any of your metadata that could be used against you. How we do it? So let me first go through some of the privacy features that enable this at HOPR, what we're building. So like I said, we build a decentralized and incentivized packet relay network, and one of the features that the network has is that we route all your data through like multiple hops. In this case, in this example, there's Alejandro who gets data and sends it to Zoe, and in this case, only Zoe and Alejandro will know who is the sender and recipient of the data or what is the content of the data, and nobody else. On top of that, we have packet mixing, which actually makes the privacy then actually superior to like a VPN, a classical VPN or even Tor. That is, this data that gets into the network are not just routed through multiple hops. They also get split up in several packages and then routed through different routes. And basically at each layer in the network, they get mixed. So which adds an additional layer of privacy to the network. The third thing, what I would say, is the really distinguishing feature of HOPR, and what I believe is what will actually make HOPR scale, is that we, like nodes who provide the service of relaying data in the network, are not doing that on a voluntary basis. They actually get paid for this. So if you relay data in the network, you get paid for this, and we do it actually through like a mechanism that we invented, which is called proof of relay. That means like when you send data in the network as a relayer, when you do your job of relaying messages, you actually don't need to trust any of the other relayers in the network. For example, if data goes through the network, then Betty in this case can only get her reward in HOPR token, which is paid through the protocol, if she gets a confirmation from Chao, in this case, which is the next downstream node in the network, that she did her job correctly and actually relayed the data. And this will actually ensures that, yeah, you don't need to trust any other node in the network, but this also ensures that you don't need to trust the HOPR association itself, because we don't store any kind of financial data, because we don't need these data to actually be able to pay people, because it all happens through the protocol by itself. A feature I want to talk about a little bit more in detail today, that's something that I have been working on, which is called cover traffic, which is basically the missing piece in the puzzle to provide full privacy in the network. And that is adding privacy via noise and incentives. So let me first give a brief introduction into cover traffic. I made this illustration, how you should imagine it. So there's somebody, and let's call it an adversary, who wants to know who's talking to each other. Because if he observed these people talking to each other multiple times, he might be able to infer what they're actually talking about and de-anonymize them. In this case, the adversary stands in front of a closed door, but in the room are only 2 users. So basically, the adversary knows that there are only 2 users let's say in the network or in this room. So actually the adversary knows that, okay, they must be talking to each other. So basically they are de-anonymized in this example. So basically this illustration reflects a network where there's really low usage. In an edge case that only 2 people are actually using the network. Where it's pretty easy to de-anonymize these people, even though all the other privacy features that I talked about previously are in place. And what does covered traffic in essence do? Covered traffic injects way more people into the room. So now, if you think about in terms of this illustration, now it gets infinitely much harder for the adversary to even figure out who's talking. That user 1 is actually talking to user 2, because there's a lot of random noise of other people here in the network or in this room talking. In essence, that is covered traffic. Basically, what it means in the summary for the HOPR network is, what we have been building is that CT blends basically random noise, random messages into the HOPR mixnet to obfuscate real communication traffic that is actually going on. So what we're doing is we're injecting traffic into the network, and basically this traffic that we're injecting, what is very important is like to the byte, is the same as the real traffic. So basically these packets that are relayed, whether it's organic traffic or covered traffic, are indistinguishable from each other from the outside. And basically that, and we'll get back to that, ensures that this is how HOPR protects real communication traffic from global passive adversaries, observing the network and compromising privacy. For example, one attack that you might know about is like an intersection attack. If we just think back of this little illustrative example from before, performing an intersection attack is very easy because there are only 2 people knowing the network, so you don't need to basically observe much of the communication to de-anonymize people. But again, performing an intersection attack becomes infinitely much harder if we, by covered traffic, ensure that there's always enough traffic in the network. This sounds all good, but there are 2 things that I wanted to highlight with the implementation of covered traffic that doesn't make it straightforward at all. The first thing is that there is something called that is the anonymity trilemma, and in each corner of this triangle, I highlighted 3 desirable features of a network. First, we want to have high privacy, right? We want to have data relayed through multiple hops. We want to have packet mixing. We want to have covered traffic. Then it's very hard for somebody observing the network to figure out who's communicating with each other. However, if we inject, let's say in terms of covered traffic, a lot of covered traffic, a network, of course, always also has a bandwidth, where the bandwidth is like the amount of data that actually can be processed by the network in a given amount of time, or the throughput. If we put too much cover traffic, then it might lead that actually we provide a lot of privacy, but we also at the same time congest the network. If we congest the network, what does that mean? Then data doesn't get relayed to the destination anymore in time, or at all. And what does it mean? Like a third desirable feature that we have in a network is low latency. Of course, then the latency gets higher. How can you basically reduce latency? Hey, you can say like, okay, I route only through 1 hop instead of 3. Or I provide less cover traffic to not congest the network anymore. So just what I'm illustrating here, what you see where I'm going is that these 3 desirable features are all interacting with each other. And basically what we're working on is to balance them out. Another thing that we call programmable privacy is we actually give the user the choice how much privacy he wants to have. For example, if you have a certain transaction where you say like, I don't really care so much about privacy, I really care that this transaction goes through very fast, then you can compromise some of the privacy for more latency. Or you think like, hey, I can wait a little bit longer, I want complete privacy. Another aspect that is very particular to the fact that we have an incentivized mixnet is that incentivizing covered traffic is just as crucial as incentivizing organic traffic within the HOPR network, right? I told you before that it's very important that covered traffic is indistinguishable from real communication traffic. That also means if nodes relay covered traffic in terms of instead of organic traffic, they also need to get paid for relaying that. So cover traffic has a cost, and somebody has to pay for it, right? What I want to highlight next is a little bit the app that I and my team have been working on. And so just to give you a brief outline of the app. So we have been working on the cover traffic app. That's the first implementation of cover traffic in the HOPR network. What we have done is we have like some nodes in the network. And to be fair, all of what I'm talking about, that's the first implementation of cover traffic. It is basically centralized as an app controlled by us. But of course, the goal is to completely decentralize it and have it not controlled by us, but we need it initially controlled by us because we want to learn from the data to actually work to a state where the end goal is that each node itself has an incentive to issue cover traffic. But for the time being, we have nodes in the network which are basically attached to, as a sidecar, have a Python script. We call them net watchers, and basically what they do is they ping all nodes in the network and should see which nodes are actually available to even relay cover traffic. These nodes send the information to what we call like an aggregator. The aggregator, the only job is basically also a Python script, and the only job of that script is to basically figure out the unique list of peers seen in the network, because multiple nodes can see the same peer, and orders them by the amount of latency that this ping has to optimize the sending of cover traffic. It's going to be sent to a database, and this database then gets read by what we call the economic handler, which basically performs the calculation of how much cover traffic a certain node should receive in the network. This gets sent to RabbitMQ, a salary broker. It's basically a message broker, which then we have another sidecar attached to the same nodes as the net watchers, which is called a postman. And this postman is then going to send out cover traffic to the nodes in the network. Why are they attached to the same node? Because the net watcher has the availability information. So basically, the same node needs then to send out the traffic to the cover traffic to the nodes in the network. And let me just stress that all what we do is open source, so you can just go to our GitHub repo and check out the code. Let me give you a brief state of the current state of the HOPR network. So currently we have more than 300 running nodes with 90% availability in the network. You can check this out on our network dashboard on network.hoprnet.org. We have many more nodes waiting in the waitlist. So that implies currently it's permissioned. So we control a waitlist where we let nodes into the network because we want to scale the network slowly to learn from the data and not run into scalability issues before really knowing that we can scale. But of course, the end goal is to have it completely permissionless, of course. We currently provide, like, since the CT app is running, like for now 2 weeks, we provide supply-side revenue for the nodes in the network and privacy. By cover traffic, you can, like I said, you can check out the code at our GitHub repo, /HOPRnet/CT research. We have currently more than 9 million HOPR tokens staked in these nodes, so they stake the HOPR tokens in the nodes. And the stake is one of the variables that is eligible for how much cover traffic they get. To get, of course, a node who has more tokens gets a higher fraction of cover traffic. And then we have currently that leads that node runners earn an APR between 10 and 15% for relaying data packages in the network. So that shows the incentivization and that actually nodes earn a good share of profit currently. Let me go lastly is that our product that launched yesterday is basically enjoy privacy with RPCH. RPCH is the first private gateway to the blockchain and provides demand-side revenue for the HOPR protocol. So cover traffic is nice to have, it provides supply-side revenue, but of course supply-side revenue is not sustainable in the current form because we as a HOPR association pay for it. But organic traffic, which I was talking about, comes from RPCH. And basically what it does is RPCH routes all requests from your wallet and responses from the RPC provider through the HOPR network. That means if you connect to your MetaMask and install RPCH, then you can send transactions without leaking your metadata, for example, your IP address through RPC providers like Infura. You can sign up for it for free at degen.rpch.net. And actually with the custom promo code that we just did for you guys, you can get it. If you sign up until 31st of October, you can get 6 months of it for free. And basically already start today to send private transactions. And yeah, that's it from my side. I think I have a little bit more time, so I can take 1 or 2 questions if there are. Yeah.
Is it available only for connecting to blockchain through a gateway, or for general purpose communications like Tor?
So basically you can connect to it, it's an SDK, so it's compatible with any EVM compatible blockchain, so you can use it on any EVM compatible blockchain. Sorry,
the question was if we can use the same infrastructure to make like an equivalent of the Tor network, but with tokens to incentivize the different proxies.
Yes, so basically, I mean, you can copy that infrastructure, right? And what makes us superior to Tor is packet mixing. So we have routing like Tor, but on top of that we have packet mixing, and what really distinguishes it is incentivization. So we don't require nodes to be run voluntarily, which in essence, we believe once we are ready to scale, we can scale up to much more than the Tor network has in nodes.
How does the usage of covered traffic slows the speed of the transaction?
That is something we are currently learning about by having it run for 2 weeks, gathering the data on it, and basically doing research on how it is. But that's exactly the question we are currently answering, and that's why it's not permissionless yet, because we need to answer these questions before we go into scaling.
All right. Thank you.
Okay. I guess that's it. Thank you so much.